Good morning, students. In the previous class, that is class 2 of the chapter Electrochemistry, I already completed the Faraday laws of electrolysis. That is Faraday's first law of electrolysis and Faraday's second law of electrolysis. So today, that is in class 3, I will try to complete the application of electrolysis, the factor affecting electrolytic conductance, electrolytic resistance and conductance, what is the specific conductance, what is the equivalent conductance, and what is the molar conductance, and some mathematical relation and problems relating to it. So before going to the class 3, let us little bit discuss about the previous class, that is class 2, that is Faraday laws of electrolysis. First law and second law. What is the Faraday first law? This law said that the quantity of substance deposited or liberated at their respective electrodes is directly proportional to the quantity of electricity passed through it. I repeat again. The amount of substance deposited or liberated at their respective electrode during electrolysis is directly proportional to the quantity of electricity passed through it. The mathematical expression is W is equal to ZIT, where Z is a constant which is known as electrochemical equivalent. Next is over to Faraday's second law. This law said that when the same quantity of current pass through the different electrolyte connected in series, then the quantity of substance deposited or liberated at their respective electrode is directly proportional to their equivalent masses. I repeat again. When the same quantity of electricity pass through the different electrolyte connected in series, then the masses of the different substances deposited or liberated at their respective electrode is directly proportional to their equivalent masses. For example, mark that. Let us consider 3 electrolytic cells which are connected in series. One contains copper sulfate solution, one contains silver nitrate solution, and one contains acidified water. Mark that. And which are connected in series. Then we observe that, mark that, this is known as CuSO4 solution. It is AgNO3 solution. It is acidified water. If we are connected in series and same quantity of electricity pass through it, then by taking the first 2 container, we observe that, what we observe? That is mass of copper deposited by mass of silver deposited, mass of copper deposited by mass of silver deposited is equal to equivalent mass of copper divided by equivalent mass of silver. Let us consider that the mass of copper deposited is W1 and that of silver is W2. Equivalent mass of copper is E1 and that of silver is E2. Then according to this law, W1 by W2 is equal to E1 by E2. Equation 1. Dividing right side the numerator and denominator of the equation 1 by 96500, we have, mark that, W1 by W2 is equal to E1 by 96500 divided by E2 by 96500. In Faraday first law, you know that equivalent mass by 96500 is equal to electrochemical equivalent, that is Z. That means W1 by W2 is equal to Z1 by Z2, equation 2. So by comparing equation 1 and 2, we observe that what we draw a conclusion, that is by comparing 1 and 2 we have W1 by W2 is equal to E1 by E2 is equal to Z1 by Z2, equation 3. It is the mathematical expression of Faraday's second law of electrolysis. So here 4 parameters are there. While solving problem, 4 parameters W1, W2, E1 into 4 parameters are in question. 3 parameters given. We have to calculate the value of 4th one. Let us apply a problem how this formula is utilized solving that problem. Mark that. A question: when the same quantity of electricity is passed through acidified water and CuSO4 solution, then it liberate 203 ml of hydrogen measured at NTP at 298 Kelvin and deposit an amount of 0.302 gram of copper. Calculate the equivalent mass of copper. Mark the question. What is the data given? Data given is a 2 electrolytic solution. One is acidified water, one is a copper sulfate solution. Same quantity of current pass through same time. Then what is given? Amount of copper is given. This is the amount of copper is given. But volume of hydrogen is there. We have to calculate the amount of hydrogen. How we solve? Mark that answer. We know that at NTP, at normal temperature and pressure, 1 ml of hydrogen weight is 0.00009 gram at NTP. Therefore, if 1 ml of this one, then weight of 203 ml of hydrogen is equal to 0.123409 into 203. Suppose x gram. Mark that. This is known as W1. This is known as W2. We know the formula. What is the formula? W1 by W2 is equal to E1 by E2. Suppose W1, mark that. Suppose W1 is the mass of copper deposited, W2 is the mass of hydrogen liberated. This one given. Then question is calculate the equivalent mass of copper. And this is not given question, but we know that is equivalent mass of hydrogen, that is 1.008, simply taken as 1. So that is E1 now. E1, that is equivalent mass of copper, is equal to W1 by W2 into E2. W1 mass of copper deposited given, W2 mass of hydrogen liberated given, E2 that is equivalent mass of hydrogen, that is 1 or 1.008. By putting this value, E1 equivalent mass of copper can be calculated. Next, switch over to today class. In today class, first we discuss what are the factors. What are the factors affecting electrolytic conductance? Next we discuss factors affecting electrolytic conductance. Electrolytic conductance. 3 to 4 points are there. 3 to 4 factors are there which affect electrolytic conductance. Point 1 is nature of the electrolyte. Point 2, size of the ion produced. Point 3, nature of the solution. Point 4, concentration of the solution. Point 5, temperature. Mark that. Point 1 is nature of the electrolyte. Next, size of ions produced. Next, concentration of the solution and its viscosity. Next, nature of the solution and viscosity. Fourth one is concentration of the solution. Fifth one is temperature. Mark that. What is the point 1? Point 1 is nature of the electrolyte, means it is a strong electrolyte or weak electrolyte. Mark that. If it is a strong electrolyte, then the degree of conductivity, degree of conductance is higher in comparison to weak electrolyte. Next one is size of the ion produced. Higher is the size, larger is the size of the ion, slower is its conductivity. Next one is nature of the solution and its viscosity. If that is the nature of the solvent, it is known as nature of the solvent. Mark that. If solvent is polar in nature, and viscosity is low, then higher is the conductivity. Next is concentration of the solution. That means higher is the concentration of the solution, lower is the conductivity. Last one is the temperature. Higher is the temperature. On increasing the temperature, degree of dissociation or degree of ionization increases. Means number of ion increases, so conductivity increases. So these are the factors affecting electrolytic conductivity or electrolytic conductance. Next we discuss what is the application of electrolysis. Next we discuss application of electrolysis. Application of electrolysis. 2 to 3 points are there. What are the application of electrolysis? 3 to 4 points are there. One is electroplating, electrotyping, electro-refining, and electrolytic extraction of metal. These are the 4 important applications of electrolysis. Mark that. Point 1 is electroplating. Point 2, electrotyping. Point 3, electro-refining. Point 4, electrolytic extraction of metal. Electrolytic extraction of metals. Mark that. Point by point. What is the point 1? Electroplating. Plating means coating. What is electroplating? The deposition of good quality of metal over the less quality. Deposition of superior metal over lesser quality metal is known as electroplating. Then why is it carried out? Generally it is carried out for three purposes. One is decoration. Second one is protection. And the third one is repairing. These are the three main aspects of the process of electroplating. I repeat again. What is the point one? Point one, that is decoration. Second one, protection. Third one is repairing. These are the main aim for the electroplating. In addition to the electroplating, next one is electrotyping. In printing press, the letter, or in typewriter, the letter are prepared by the process of electroplating. Next one is electro-refining, purification by the help of metal, by the help of electrolysis. Last one is electrolytic extraction, means extraction of metal from its ore by the process of electrolysis is known as electrolytic extraction of metals. These are some applications of electrolysis. Next we will discuss electrolytic resistance and conductance. Next we will discuss electrolytic resistance and conductance. Under this heading, first one is Ohm's law. What is this law? This law states that the strength of the current, symbol is I, the strength of the current passing through a conductor is directly proportional to the potential difference, symbol of V, applied across the conductor, and inversely proportional to the resistance R developed. I repeat again, this law states that the strength of the current passing through a conductor is directly proportional to the potential difference, symbol is V, and inversely proportional to the resistance, symbol is R, applied, developed across it, mark that. The strength of the current passing through a conductor is directly proportional to the potential difference and inversely proportional to the resistance. If we write mathematically, the mathematical expression for this Ohm's law is I is equal to V by R, where I is known as the strength of the current expressed in ampere, V is the potential difference measured in volt, and resistance is R is the resistance expressed in ohm. It has been observed that the resistance developed across a conductor is directly proportional to its length of the conductor and inversely proportional to its area of cross section. I repeat again. The resistance developed across a conductor is directly proportional to its length and inversely proportional to its area of cross section. So if we express it mathematically, what is the mathematical expression? If we represent this one in form of mathematically, then it has been observed that is resistance R proportional to L proportional to 1 by A, that is inversely to area of cross section. So by combining this one R proportional to L by A, if we remove the proportional sign, R is equal to a proportional constant R rho into L by A. Mark that, equation 1. R is equal to rho is a proportionally constant which depends upon the nature of the material taken into L by A. This proportionally constant is known as specific resistance. Rho is known as specific resistance or resistivity of a conductor. So mark that. It is a proportionally constant which is known as specific resistance or resistivity of a conductor. So from this definition, now we can frame one. From this relation, we can frame one definition. Mark that. When L length is 1 centimeter, cross-sectional area is 1 centimeter square, then specific resistance rho is equal to R. Mark that. When L is equal to 1 cm, A is equal to 1 cm square, then rho is equal to R. So from this one is able to deduce one expression, that is the specific resistance or resistivity of a conductor is defined as the resistance developed. The specific resistance or resistivity of a conductor is defined as the resistance developed when length of the conductor is unit, length is unit and its cross-sectional is unit, length and its cross-sectional, that is volume also is unit. Length is 1 centimeter and area is 1 centimeter square. Then the resistance developed is known as the specific resistance or resistivity. Mark that. Then we calculate from this expression rho is equal to R into A by L. Mark that. If we go through the unit of length is known as centimeter, area centimeter square, resistance that is ohm. Then what is the unit of the specific resistance? Unit is ohm dot centimeter. The unit of specific resistance is ohm dot centimeter. Next we discuss another term, that is conductance. Next we discuss another one term that is known as conductance. Conductance, symbol C. What is conductance? What is conductance? It is a special property of a conductor. It is a special property of a conductor as a result of which it allows the passage of electricity through it easily. Normally, conductance is a reciprocal of resistance. Mathematically, mark that. Mathematically, C is equal to 1 by R. We know that previous one R is equal to rho into L by A. So putting the value of resistance from this equation in this equation, we have C is equal to 1 by rho into A by L. Mark that. Putting the value of R from the equation here, so C is equal to 1 by rho into A by L. This reciprocal of specific resistance or C is equal to kappa into A by L. Mark that. That is equation 2. Mark that this is known as a constant which is known as specific conductance. Specific conductance or conductivity. This specific conductance is also the reciprocal of specific resistance. Reciprocal of specific resistance is another constant known as specific conductance or conductivity of a conductor. So rewrite this expression, we have kappa is equal to C into L by A. Mark that. If length is 1 centimeter, area, cross-sectional area is 1 centimeter square, then specific conductance is equal to conductance. Mark that. If L is equal to 1 cm, A is equal to 1 cm square, then kappa is equal to C. So from this mathematical expression, one is able to deduce one definition that specific conductance or conductivity of a conductor is defined as the conductance when length of the conductor is 1 centimeter, cross-sectional area is 1 centimeter square. In case of electrolyte, specific conductance also defined as the conductivity ability of the electrolytic solution when it is placed between the two electrodes separated by unit length and having cross-sectional area is unit cross-sectional area. So from this definition, mark that we have to calculate the unit of specific conductance. That is, unit of specific conductance is the conductance C. Normally it is a reciprocal of resistance. The unit of conductance is ohm inverse. In SI system, it is that is Simon S. 1 S is equal to 1 ohm inverse. So its unit is ohm inverse. That is centimeter inverse. In SI unit, in SI system, it is Simon and meter inverse. Mark that. This is the unit of the specific conductance. Another important thing is that mark that this L by A is also known as another one constant that is known as cell constant. So from this relation we can also calculate specific conductance is equal to conductance into cell constant, or specific conductance by conductance is equal to cell constant. Mark that, it is an important relation. 3-mark question is there. What is the 3-mark question? Prove that specific conductance by conductance is equal to cell constant. Mark that this relation is specific conductance, kappa is specific conductance, by conductance is known as cell constant. So from this L by A is known as cell constant. So what is the unit of cell constant? It is known as cell constant, its unit is centimeter inverse. Now we have to go through solving a problem, how this formula is utilized in solving a problem. Mark that. The formula is kappa is equal to C into L by A. Mark that, it is a formula where C is known as conductance. So we can rewrite this formula, that is kappa is equal to 1 by R into L by A, because the resistance is known as reciprocal of conductance. So mark that, what is the type of question? The specific conductance of N by 50 KCl solution at 298 Kelvin is 0.0023 ohm inverse, Cm inverse. I repeat again, the specific conductance of n by 50 KCl solution at 298 Kelvin is this much if the resistance of this cell is 100 ohm. Calculate the cell constant. Calculate the cell constant. Answer. Mark that. What are the data given? Resistance given. Resistance. Answer given. Given that resistance R is given, that is 100 ohm. Next, specific conductance kappa is given 0.0023 ohm inverse centimeter inverse. These two data is given. Question is calculate the cell constant L by A. Mark that. If we apply this formula, that is cell constant L by A is equal to kappa into R. Mark that. Cell constant L by A is equal to kappa into R. Kappa, value of kappa is given, value of resistance is given. If we multiply this value, then the answer is cell constant. Next, switch over to another one is there, that is known as equivalent conductance. Next we discuss about another one term is there, that is known as equivalent conductance. Very important one for council point of view, that is known as equivalent conductance. Symbol lambda EQ. What is equivalent conductance? What is the definition of equivalent conductance? It is defined as the conducting power of all ions produced. It is defined as the conducting power of all ions produced by dissolving 1 gram equivalent of the electrolyte in solution. I repeat again. It is defined as the conducting power of the solution, dissolving 1 gram equivalent of the electrolyte, conducting power of all the ions, produced, by dissolving 1 gram equivalent of the electrolyte in solution. Mark that. Equivalent conductance is defined as the conducting power of all the ion produced by dissolving 1 gram equivalent of the electrolyte. If, mark that, if VEQ is the volume of the solution containing 1 gram equivalent of electrolyte, then according to the definition, that is lambda EQ is equal to kappa into VEQ. Equation 1. Mark that. Where kappa is known as a specific conductance and VEQ is the volume of the solution containing 1 gram equivalent of the electrolyte. If C is the concentration, mark that. If C gram equivalent of electrolyte present in 1000 cc of the solution, then the volume of the solution, then the volume of the solution containing 1 gram equivalent of electrolyte. 1 gram equivalent of electrolyte is, that is VEQ is equal to 1000 by CEQ. Equation 2. Mark that. C is known as the concentration of the solution containing 1 gram equivalent of the electrolyte. So putting the value of VEQ, from equation 2 in equation 1, we have, mark that, what we have? That is equivalent conductance, that is lambda EQ, equivalent conductance is equal to kappa into 1000 by CEQ, where C is the concentration per 1 gram equivalent. When 1 gram equivalent is there, solute is there, electrolyte there, then the better way to express the concentration is in normality. Hence, the our equation becomes equivalent conductance is equal to kappa into 1000 by N. Equation 3. Mark that. Where N is known as a normality. N is normality is equal to W into 1000 by E into V in ml. And the most important thing is that the unit. The unit of equivalent conductance is ohm inverse cm square gram equivalent inverse. The unit of equivalent conductance is ohm inverse cm square gram equivalent inverse. Next, we go through one problem, how this formula is utilized in solving the problem. What is the formula? I repeat again, that is formula is equivalent conductance is equal to kappa into 1000 by normality. Again, what is kappa? Kappa is known as specific conductance. That is C into L by A into 1000 by normality. Again, what is C? That is known as conductance. I can replace conductance by resistance. It is the reciprocal of resistance. That means another formula also there. Equivalent conductance is equal to 1 by R into L by A into 1000 by normality. These are the different way of expressing the formula method relation for equivalent conductance. Now it is our time to go through one problem solving how this formula is applied for solving a problem. Go through a question, mark that. Question. 0.5 N NaOH solution, 0.5 N NaOH solution when placed in a cell having length of the electrode is 20 centimeter and its cross-sectional area is 4 centimeter square. Afford a resistance of 100 ohm. Calculate the equivalent conductance. Calculate the equivalent conductance. Mark the question. What are the data given? 0.5 normal sodium hydroxide solution placed in a cell having the length of the conductor electrode is, that is 20 centimeter. Cross sectional area of the electrode is, that is 4 centimeter square. Offered a resistance of 100 ohm. So mark that. Answer. What are the data given? Given that L is equal to 20 centimeter, A is equal to 4 centimeter square, resistance, that is R is equal to 100 ohm, and concentration normality is equal to 0.5. Question mark lambda eq is equal to question mark. So our aim is to find out the equivalent conductance. Mark that. What is the equivalent conductance? 1 by resistance into L by A, that is cell constant, 1000 by normality. Mark that. Resistance given, L given, A given, and a normality given. So by putting this value, one is able to calculate the equivalent conductance of the electrolytic solution. Next we switch over to another one term is there, that is known as molar conductance. Next we discuss another important one is there, that is known as molar conductance, symbol lambda MOL. What is the definition of molar conductance? Like equivalent conductance, it is defined as the conducting power of all the ion produced by dissolving 1 mole of the electrolyte in solution. In equivalent conductance, 1 gram equivalent of the electrolyte. In molar conductance, 1 mole of the electrolyte. I repeat again, it is defined as the conducting power of all the ions produced, conducting power of all the ion produced by dissolving 1 mole of the electrolyte, 1 mole of electrolyte in solution. Mark that. If V mol is the volume of the solution containing 1 mole of the electrolyte. I repeat again. If V mol is the volume of the solution containing 1 mole of electrolyte, then the mathematical expression, that is lambda mol, molar conductance, that is molar conductance is equal to kappa into V mol. Mark that. The mathematical expression, molar conductance is equal to specific conductance into V. What is V mol? V mol is the volume of the solution containing 1 mole of the electrolyte. Again, if C mole of electrolyte is present in 1000 cc, next is mark that. If C mole of electrolyte is present in 1000 cc of solution, then the volume of electrolyte, present, the volume of the electrolyte containing 1 mole of electrolyte, that is VMOL is equal to 1000 by CMOL. That is equation 1. It is equation 2. What is C? C is known as the concentration. When 1 mole of electrolyte is there, then it is better to represent, that is molar solution or molarity. If we apply this one, then above equation becomes, mark that, if we apply the value of V from equation 1, in equation 2 we have lambda MOL, molar conductance is equal to kappa into 1000 by C MOL. Mark that. Now C, concentration is better way to express, that is molar solution, molarity. That means molar conductance is equal to kappa into 1000 by M. Equation 3, where M is known as molarity. Its mathematical expression W into 1000 by M into V in ml. Weight by molecular mass into 1000 by V, volume in solution, in ml. So most important thing is that similarly equivalent conductance, the unit of a molar conductance, unit is ohm inverse Cm square mole inverse. Very important. What is the unit of a molar conductance? The unit of molar conductance is ohm inverse Cm square mole inverse. Next we go through solving a problem by the help of this formula. How to calculate molar conductance. Before solving the problem, I write this formula, that is lambda MOL is equal to kappa into 1000 by molarity. So in alternative way to express for simplifying, that is, or lambda MOL is equal to 1 by R, kappa is equal to C into L by A, 1 by R into L by A into 1000 by molarity. R is known as the resistance, L by A is known as the cell constant, M is known as the molarity. So what is the question? Question, that is 0.1 molar potassium hydroxide solution at 298 Kelvin afford a resistance of 32 ohm if the cell constant is 100 cm inverse. Calculate the molar conductance. Calculate the molar conductance. Mark the question. What are the data given? Data given. Mark that. Answer. Data given. 0.1 molar, that is molarity 0.1. Offered a resistance, that is R is equal to 32 ohm. If the cell constant, that is L by A, cell constant 100 cm inverse, calculate molar conductance lambda MOL is the question mark. Mark that. A formula is there, we know the formula. Molar conductance is equal to 1 by R into L by A into 1000 by molarity. Resistance value is given L by A. L by A is known as the cell constant. Cell constant value given. Then molarity, molar solution, molarity 0.1 given. So this value given, this value given, this value given. So by putting the value, one is able to calculate the molar conductance. The most important thing, I repeat again, the unit. The unit of equivalent conductance is ohm inverse cm square gram equivalent inverse, and the unit of molar conductance is ohm inverse cm square mole inverse. Next we discuss the relationship between equivalent conductance, molar conductance and specific conductance. Next we discuss the relationship between equivalent conductance lambda IQ, molar conductance lambda MOL, and kappa, that is specific conductance. What is the relationship between equivalent conductance, molar conductance and specific conductance? So already we have find out that the relation, that is expression for each one, that is, mark that equivalent conductance is equal to kappa into 1000 by N, equation 1. Molar conductance, that is lambda MOL, is equal to kappa into 1000 by M, equation 2. That means equivalent conductance related to specific conductance, molar conductance also related to specific conductance. So dividing equation 2 by equation 1, mark that. Dividing equation 2 by equation 1, we have, mark that, molar conductance by equivalent conductance is equal to kappa into 1000 by M into N by kappa into 1000. Cancel out. That means molar conductance by equivalent conductance is equal to normality by molarity. Very important one. That means molar conductance, very important one. Molar conductance by equivalent conductance is equal to normality by molarity, and is also is equal to N, that is known as, what is N? N is known as valency factor. The most important thing is that equivalent conductance by molar conductance is equal to normality by molarity is equal to N. N is known as valency factor. What do you mean by valency factor? It is the, for acid it is the basicity, for base it is the acidity, and for salt it is the total number of valence of the cation or anion. For example, if we discuss about HCl, then its valency factor N is equal to, it's 1. Means it is acid, so its basicity is 1. For H2SO4, it is acid, so basicity is 2. That is for sodium hydroxide, it is a base, its acidity is 1. Mark that. For aluminum chloride, mark that. For aluminum chloride, it is a salt, total valence of cation, that is N is equal to 3. Mark that. Another one. For aluminum sulfate, Al2SO4 whole thrice, here also valence factor is 6. The total number of cation or anion. I repeat again. Valence factor, it is, for acid it is the basicity, for base it is the acidity, and for salt the total number of cations, the total valence of the cation or